Hi, thanks for watching this video. I'm Xifan, and I will talk about the computational hardness of detecting random graph lifts and certifying properties of random regular graphs. This is joint work with Team Kunisky. Let me introduce the setup of certification and refutation of properties for random graphs through the example of maximum independent set. There are two natural problems associated with the maximum independent set. One is to search for a large independent set, and the other is to certify an upper bound on all independent sets. This talk will focus on the average case hardness of certification, specifically over the distribution of random regular graphs. To be more precise, we consider the input to be drawn from the distribution of random regular graphs, denoted as G and D, and we want to output a true bound Bg that always upper bounds the independence number of G. We call such an algorithm a certification algorithm. How do we measure the quality of such an algorithm? We know that the independence number will concentrate around its expectation for graphs drawn from the distribution of random regular graphs. So we want the certification algorithm to output the bound as close to this expectation as possible. And we also require this algorithm to output a bound that holds for every input. And moreover, we want this bound to be efficiently computable. And here are some more examples for problems of this flavor. Besides independence number, one can also ask the same question for chromatic number, small set vertex expansion, and small set edge expansion. And from random graph, using tools from random graph theory, we have a good bounds and estimates of the expectation of these numbers for the distribution of random regular graphs. We also have some kind of certificate for each of these graph properties, but very often these two numbers, they do not agree. And this work attempts to address this disparity and give some evidence that why perfect certification is impossible in some cases. We'll come back to this table later on. The main result of this paper is as follows. We propose a new conjecture about the computational hardness of detecting random graph lifts, which in turn implies the certification bounds for the examples shown in the previous slides are essentially optimal. We also provide evidence for the proposed conjecture using hardness against the so-called local statistic hierarchy. And we also set forth a general framework for deriving hardness of certification problems using this conjecture. So our work follows this general idea of quiet planting, which uses the reduction from a specific hypothesis testing problem to the certification problem of interest. To be more precise, let us consider we want to certify a bound of some alpha for some generic alpha x when x is drawn from distribution Q. The strategy is to plant some special structure in X to create a planted distribution. And suppose that after planting this special structure, the value of alpha x will be unusually large compared to its typical behavior for under the distribution Q. And moreover, suppose that these two distributions P and Q are computationally indistinguishable. These two assumptions will allow us to conclude that it is computationally hard to certify a bound on alpha x better than this threshold TP minus epsilon for x drawn from the distribution Q. Since if we do have an efficient procedure to do so, we can use this certification algorithm to distinguish the two distributions P and Q. So this quiet planting idea, our quiet planting idea is inspired by this work where they consider an equitable stochastic block model as their planted distribution. And they conjecture that it is hard to detect this distribution P from the random irregular graphs, through which they derive hardness of certification for maximum K-cut. And we observe that their equitable stochastic block model actually falls under the umbrella of random graph lifts. And this is the basis of our work. We consider random lifts of Raman-Nugent graphs as our planted distribution P, and we conjecture the conjecture that it is hard to detect random lifts of Ramanujan graphs from random regular graphs. And using this, we derive hardness of certification for independent sets, chromatic number, small set expansion, and more. So what is a graph lift? We say G is an M lift of H if vertex set of G can be partitioned into sets of equal size, each of size M, and moreover, for every edge, for every edge of H, the corresponding sets Si and Sj induce a perfect matching in G. For every non-edge in H, there are no edges between the corresponding Si and Sj in G. The following is a pictorial illustration of a graph lift. On the left, we have a complete graph of K4, and on the right is a 3 lift of K4, where we replace each vertex by a bubble of 3 vertices, and we replace each edge by a perfect matching between the corresponding bubbles. To generate a random lift, we simply replace each edge of H with a random matching in G. So graph lifts have some nice properties that allows us to design the quiet planting strategy. Let G be an M lift of H. It is clear that if H is deregular, G will remain to be deregular. And moreover, every eigenvalue of H will again appear as eigenvalues of G. And moreover, graph lifts enjoy additional structure preserving properties, such as G is k-colorable whenever H is k-colorable. If H has a large independent set, G also has one. If H has a non-expanding set, G also has one. And these properties inspire us to use the following idea to hide un-Euro structure in random lifts of H. But one question we need to address is when can we expect random lifts denoted as LMH to be hard to distinguish from the random regular graphs? We'll claim that at least it needs to be spectrally quiet, in the sense that the distribution of spectrum of the random lifts should look the same as that of the random regular graphs. What do we know about the spectrum of random lifts and random regular graphs? It turns out both of these questions have been answered. For random regular graphs, G has spectrum converging to the Caston-Mackay distribution supported on -2 square root d minus 1 and 2 square root d minus 1, besides the trivial eigenvalues plus minus d. For random lifts of H, as M goes to infinity, the spectrum of G drawing from an M lift of H converge to the spectrum of H plus a spectrum converging to the Caston-Mackay distribution. So from these two theorems, we see that whether the spectrum looks the same depends on the edge of the spectrum of H. So this brings us to the definition of Ramanujan graph. A deregular graph H is Ramanujan if its non-trivial eigenvalues are bounded by 2 square root d minus 1 in magnitude. And from the theorems on the previous slides, if H is Ramanujan, then LMH will be spectrally quiet from the random regular graphs, since the spectrum of H would be engulfed by the Caston-Mackay distribution. Whereas if H is not Ramanujan, it is easy to distinguish the random lifts of H from random regular graphs simply by looking for an outlier eigenvalue. So our main conjecture of the work is the following. If H is Ramanujan, we conjecture it is computationally hard to distinguish a random lift of H with a small amount of adversarial edge flip from the random regular graph. To just a few remarks about the adversarial edge flip. This adversarial edge flip is there in order to stop algorithm from exploring brittle structures such as the existence of a specific eigenvalue of H or the structure of some specific eigenvectors of H. For more convincing evidence of the conjecture, we look at a variant of sum-of-squares algorithm for hypothesis testing. This is the local statistic algorithm. The high-level description is that this algorithm essentially looks for a pseudo partition that mimics the partition of the underlying graph lift. And by design, this algorithm succeeds on input drawn from random graph lifts. If the algorithm fails on input drawn from the random regular graphs, we say that it distinguishes the random lifts from random regular graphs. To formalize this algorithm, one can use the pseudo expectation operator and ask it to satisfy a number of pseudo moment constraints inspired from pseudo calibration technique. This was introduced in the paper of Banks, Mohanty, and Raghavendra, and proved to be a useful, robust algorithm for stochastic block model detection. Our main theorem about the local statistic hardness is as following. Sorry that I don't have enough time to define the local statistic algorithm properly. We prove that if H is Raman-Nugent, then the degree 2 order 1 local statistic algorithm fails to distinguish the random lifts of H from random regular graphs. On the other hand, if H is not Raman-Nugent, then degree 2 order 1 local statistic algorithm distinguishes the random lifts from random regular graphs, even after a small linear amount of adversarial edge change. Finally, let me discuss the consequences for the certification of random regular graphs. We define a function that maps deregular graphs to real numbers. We call it to be lift monotone if f of any lift of h is at least as much of f of h. And we further say f is robust if f does not change too much after a small linear amount of edge changes. Some examples of such functions include the normalized independent set and the delta vertex expansion, which is equal to the minimum vertex expansion of all sets of size at most delta n. So the main theorem in this of consequence of certification is as follows. Let f be a robust and lift monotone function, assuming the main conjecture. Then for any Raman-Nugent graph H, it is computationally hard to certify a bound fg is at most fh minus epsilon for graph G drawn from the random regular graphs. The upshot is that to find good conditional lower bounds for certification, it is enough to optimize f over small Raman-Nugent graphs. And next, we will see some examples of this theorem, of application of this theorem. First, let us consider the minimum dominating set. Just a reminder that a set is called the dominating set if every vertex in V minus S is dominated by some vertex inside S. And the true value of this number for random deregular graphs is on the order of n times log d over d. Whereas we have a trivial certification algorithm that says you need at least n times 1 over d plus 1 vertices in order to dominate to get a dominating set, since every vertex can dominate at most d plus 1 vertices. To exhibit hardness, we consider the Raman-Nugent graph kd plus 1, which has a dominating set of size 1. Using our theorem, we can show that under our conjecture, it is hard to certify a bound for the dominating set better than n times 1 over d plus 1 plus epsilon. We can also consider examples for maximum independent set of a fixed degree equal 4. In this case, the true value of the normalized independent set lies within the interval 0.404 and 0.412, whereas Hoffman's spectral bound certifies a bound roughly 0.464. And using the example below, we show that it is hard to certify a bound better than 0.428 by observing the 3 vertices in the middle form an independent set in this Raman-Nugent graph. And then finally, let us consider the small set vertex and edge expansion. And we'll just consider the vertex expansion for simplicity. This quantity is defined as the minimum vertex expansion over all sets S of size at most epsilon n. The true value of this quantity is close to d minus 1 s for epsilon small enough. And the state of our certification algorithm we consider is a Cahaly spectral bound, which proves that this this vortex, a small set vortex expansion is at least d/2 times something very close to 1 as epsilon goes to 0 and as g, and for Ramanujan graph G. For graphs G with eigenvalues with eigenvalues close to with non-trivial eigenvalues at most 2 square d minus 1 plus little o1. And we can use the Ramanujan graph from the Cameron-Kaufman result to show that it is actually hard to certify a bound better than d/2 plus delta. But we remark that this only works for the bipartite case, and for degree d, that is a prime power plus 1. And a similar story goes for the edge expansion, and one can show that for some specific cases, the highest bound is also optimal. In summary, we propose a new framework for proving conditional hardness of certification for random regular graphs, and we established optimality of a number of benchmark certificates. We also provided evidence for the main conjecture using the local statistic hierarchy. Some open problems in this direction include proving higher degree local statistically lower bound and showing other forms of evidence of hardness coming from sum of squares, low degree polynomials, or local algorithms. More applications of this quite punting idea for non-lift monotone functions and analysis of the effect of random lifts on specific graph properties would also be interesting. That's all for my talk. Thank you.